Hi, Michael. Welcome back.
Yeah, hi Adam. Nice to see you again. Yeah.
I mispronounced your name. It was Michael?
It's Michalis, but yeah,
Mihalis,
yeah,
exactly.
yeah,
Mihalis, exactly.
yeah.
Um, how warm is it in your country right now?
Well, right now I'm in Greece, so it's about 35 degrees.
35, okay, it's similar
Yeah,
to Germany.
yeah,
Yeah. GPU Llama.
yeah,
So the entire story was that the Alfonso had a nice GPU, Llama 3. So what Alfonso did, Alfonso ported CPP, Llama CPP to Java and used SIMD. So on my machine, we could get 10 tokens per second with a quantized Llama model. And then you both got in touch. And what you did, or your team did, is you have now a GPU accelerated version of Alfonso version. And what I learned the last time is it was really hard to optimize because the SIMD was already fast and Tornado was not meant to be optimized for LLM, but now it is. So maybe the first step. So if you got the source code from Alfonso, we look at this. It was one file with SIMD. It is like I would say an ugly way to have very fast matrix multiplications in Java. So ugly means unusual way, maybe. So if you see this the first time, you say, okay, what's going on here? So what was the story? So you saw this and or your team, and what you tried first?
yeah. So I think Alfonso's implementation it wasn't that ugly because what he did is that he managed to, let's say, compact the whole inference in just a single file. And if you compare it with the OpenJDK, let's say, I think with the array class, for instance, it's about the same size. So one can imagine that you can do the inference and have it
No,
just
Alfonso code was perfect. What I meant as ugly is the SIMD API, right? So if as Java developer, if you see the vector multiplications the first time, it's
yeah,
unusual to say what's going on, why there's so much code, why is not just the multiply sign. And the reason being is because behind the scenes a lot of happens. So you are already accustomed to this, but if I show the code
yes.
to enterprise developers, they will see what they are doing here, right? It's not obvious.
Yes. Well, for us, actually, that was the good part of the implementation because as the whole team, we've been working in Tornado for a few years now. We are kind of being familiar with this kind of mindset, trying to get the Java code and try to optimize it for hardware. So when we saw how he implemented the matrix vector multiplications on the Llama, we we were sure that this is the kind of the workload that it's good for Tornado. Um, so how it started, it was that initially our initial thought it was to profile the application, so to profile the inference and try to find out the bottleneck in terms of computation, and indeed it was the math moves. So in the very first port, what we did is that we said, okay, we are happy of running on the CPU the other part of the inference, and just what you call the ugly parts. We're gonna get the ugly parts and handle it through Tornado and offload them to the GPUs because we know that matrix multiplication is a good example for running on the GPUs. And then in this initial port, this is what we did. So we just uploaded the most computationally intensive matrix multiplication into the GPU through Tornado, and we got some initial findings. That
But
was
so what you did, you replaced the SIMDs from Alfonso with something different, right?
exactly. So as I mentioned already, Tornado has its own data types, which are based in Panama. So for Alfonso, he was using already the Panama, and he was using Vector API combined with memory segments. So he was operating the SIMD operations directly to the memory segments. So for us, it was a clear cut that okay, we're gonna copy the segment into a Tornado data structure. We're gonna copy the data onto the GPU, and then we're gonna do the computation onto the GPU and commit the data back to the CPU. And we did that last year for Llama 2, and the initial findings was that okay, we were getting some speed up compared to this SMD implementation. So for us, it was obvious that, okay, there is more space for optimization. So we had to start thinking how we can move the whole inference, the whole algorithm of the inference in the GPU. Because what we were doing back then, it wasn't very optimal, because every time you had to copy into a segment and copy also to the device the new data to perform the final, let's say, matrix multiplication in the inference. So we had a lot of I/O that it was necessary without doing all the compute required. And that's the point that we start thinking about how we can evolve Tornado and make it, what kind of extensions we require to be able to express more, let's say, complex pipelines and more complex problems like the inference. And
I have one question.
yeah.
So the my understanding is of the vector API in Java, the SIMDs, that it is that way because the Java compiler, the hotspot is aware of the API. It sees the multiplications, able to write specific instructions for Intel or AMD. So in theory, would be possible to take the vector API and the compiler could generate Tornado capable code, right? So in theory, could.
Indeed, and actually, it's something that our team thought about that, and it's actually in our backlog. So we wanted, because we have right now, what's happening is that we have our own vector API, let's say in Tornado. So if one goes and dives into our API or into the documentation online, they're going to see that we have our own, let's say, flavor of vector API that was intended back then because it was one of the first extensions of Tornado to do vector operations on to GPU, CPU integrated graphics. So we had that already, and it was one of the things that we're discussing at some point, that maybe it makes sense to support the vector API to be compatible with the Tornado API. Yeah.
Yeah, okay. Interesting. So because then it would be, we could have one API and switch, between Tornado and CPU back and forth. Okay. But so what you did is you started with the CPU and then you ported the parts to Tornado data types, and then it became already faster, right?
Yeah. So that was our initial findings. We had a presentation in DevOps UK last year about how we had this hybrid model, and we said, okay, that the idea back then was that, okay, Tornado, let's enable Tornado in your application just only when it makes sense. So we had this hybrid inference of part of it running on the CPU through through vector API memory segments, this highly optimized code that Alfonso provided. And when we hit the computational bottleneck, that was the final matrix multiplication, that it goes through the whole vocabulary in order for you to get your token, the token needed in each iteration, that we hit this bottleneck. Let's offload this part onto the GPU, and it makes sense back then. And we had some speed ups about, I think, 20 to 40% just by offloading one kernel. And if you have seen the actual implementation in the inference, you would see that you have multiple instances of matrix vectors with different sizes and stuff. And we just got about 20 to 40% speed up just by offloading one. So that was, let's say, our baseline, and we started thinking, okay, we need to find ways to move more of the computation onto the GPU, but also we had another problem to solve: how to improve the I/O, how we can reduce, the amount of times that we copy data into the GPU and the amount of times that we read the data. And through this process, Tornado evolved much in the final year. So we extended the API, the runtime, and many things in order to achieve the performance we achieved with the GPU Llama.
So what I understood is you are able now to keep the data on GPU longer than before, right? Because you had a copy back and forth, and now you can say, hey, data remain on the GPU, and then you are saving the transfer costs, right?
Exactly. So Tornado has this concept of a task graph. So you have a task graph which is a, let's say, self-contained entity of computation. So that in a very high level, the idea of the task graph is that you copy in data, you do computation for one or more tasks, and then you copy out the data. And you can copy out the data either on demand, say, okay, I just want to copy it after some execution, or every time that you execute it, or just once. You have this kind of flexibility. But the task graph is a self-contained entity, and then you have an execution plan which is responsible for executing these tasks. And you can combine multiple tasks in one execution plan and execute them. But what was happening is that you didn't have any notion of connecting to different task graphs between them. So all the data and all the references of the objects used in the first task graph, they couldn't be used in the second one. So it was very difficult, let's say, to express complex pipelines if we wanted to do something like, for example, if I have a task A and I want to execute it in a loop of 10 times, and then I want to use some data that I have already computed, what I had to do is that I had to copy out the data from the first task back to the host, and then explicitly copy them back onto the GPU.
So the loop was executed on the host then, back then?
The loop, yes, but every time that you were invoking the Tornado task graph, it was executing the kernel onto the GPU.
Yeah, the kernel was executed on the GPU, but the for loop was driven by the host, and data was copied for every iteration between host and the GPU, right?
Exactly.
Mm-hmm.
So if you have seen the
how expensive is the copy of the data? So from
that depends on how much data you want to copy.
Mm-hmm.
So because there's a trade-off about the amount of data that you want to copy in, that also it depends on the device. So if you have a device that used to PCIe, what kind of speeds they're available, and these kind of things. So it really depends of your hardware and of your data that you're actually using.
Mm-hmm. Okay, but you were able then to keep the data on Tornado. So what you did, or how you did it?
Yes, so back then we weren't able to do that. And if you have looked into the algorithm of the inference, is that for each layer, let's say that you have, for example, each model has a different number of layers. So you can go from a small amount of layers for a small model of 4 up to 64, let's say, number of layers. You do repetitive computation. So inside you have to do a number of matrix multiplication, number of normalization, number of copies, a number of attentions. And as the model grows, this number grows. And what's happening is that after you execute this loop of computation per layer, you have the final, let's say, matrix multiplication, which is when it traverses the whole vocabulary, which is a very big chunk of data. It can be gigabytes, and produces the token, the predicted token. So for us, what we wanted to have is that we want to have a way to express that some computation is going to run in a loop. I'm going to mutate the data inside there, and then afterwards, I want to keep the data onto the device and consume it by the next task graph that it does the final computation. So we want to be able to express this kind of complex pipelines that you have data that they change states between task graphs and then consume from each other. And what we did start is because the Tornado memory API back then, it was very explicit, so you can either copy in data and copy out data. That was the only thing you could do, and it was either copy out the data on demand or automatically. We introduced two different concepts in the API level and in the Tornado bytecode level in the runtime. That was the concepts of consume and persist. So now what's happening is that when you are defining your task graph and say, I want to copy in this buffer and then I want to do this kind of computation, this task, then instead of copying out the data, we say that persist object A. And then when we have defined the second task graph, we say that instead of copying the data for this task graph from the host, consume this object from a reference from the task graph. So it means that you can express more complex pipelines, and you are avoiding to do this kind of excess I/O and passing the data back to the host and to the device in order to reuse it from the second task graph, for example. And
almost functional programming, almost, or reactive, right? So this and this and this and then this. Yeah.
Yes. So it became a more explicit way to do the memory
Mhm.
management for the GPU because yes, we want the user to have control and be able to having this expressiveness in the API level.
Yeah.
And yes, and actually that's a point where we found out that we got a lot of performance for Llama 3 because we just reduced so much the communication with the CPU that for every token that we generate, we copy just one array in the beginning and just we copy out the generated token, which is exactly equivalent with what you're going to see in a pure CUDA implementation. So now one that might take a look in the how the GPU Llama is implemented and the Tornado layer planner. This is the class.
Mhm.
If someone sees how the inference is implemented in Tornado, is exactly equivalent with CUDA implementation or an OpenCL implementation. So someone who has some exposure to GPU programming, they would understand what they see. So we don't have any, let's say, gimmicks, or we don't have
Mhm.
any other, you know,
Mhm.
um, any other indirections. So it's much closer to the actual GPU programming.
What I'm wondering, because for me, as a my naive point of view, is this is how it will start. Because if I look at the model, there are layers and everything, but actually you have input and output. So there is you don't have to move the data back and forth between the host machine and the GPU. My question is, why TornadoVM at the beginning was different? You know what I mean? Why you
Uh,
had why you had to not why you wanted to copy the data back and forth? Which other use cases are there where this
uh,
is interesting? You know what I mean? Because if I would start with it in GPU, I would say, okay, cool. Hey, GPU, this is the model, this is the graph. Do it. Give me the result, right?
I think because it originated from the kind of application that we're running, so we never stepped into this kind, let's say, of semantics for an algorithm. So the main problem was that you had to run some of the computation in a loop,
Mm-hmm.
okay, multiple times from the host side, and then you had to reduce the data from a different task graph with a different semantic. So we never faced this kind of a problem before.
Which
So,
workloads you run before? So there was like one layer or what?
no, but what's happening is that Tornado actually it's used in production right now.
Yeah,
So the European Space Agency
yeah.
actually uses Tornado for the simulations. Uh,
But how
um,
they are different to LLM? What they are doing?
I think the difference that in LLM you don't have it's not a compute bound problem, it's a memory bound problem. So usually the default way that someone would use Tornado, it would be for something that it's straightforward only compute. So let's say that you have something like it's heavily uses linear algebra like DFTs
Ah,
and yes.
there are databases, for instance, and what they do, they use SIMDs for speed up for index searches or whatever, right? So the time series databases, for instance, and what they do is to compare, to have some calculations on the time. They use SIMDs to speed up. So in this particular case, I could use Tornado to run this thing on GPU, and then I would just call for whatever I do in Java, Tornado, and it will be much faster. But this is not like, yeah, you're right. So Tornado VM before was CPU accelerator, more or less, right? So you gave the algorithm, it was crazy fast and got it back. And with LLMs, it changed because they are huge, 4 gigs or more. So, and what you're doing, you're calculating like crazy, but you're actually multiplying float. So this is a complete different use case, right?
Yes. So you do, yes, exactly. So with LLMs, it's not that you're having so heavily compute problems. It's not like a computational that much intensive because you are doing like matrix
Mm-hmm.
multiplications, you are doing normalization, which has scales. So you don't do so much computational intensive things. But you have to be very precise with what you're doing with your data. So it's all about data management. That's why not LLMs. It's all about quantization. So this is what actually made LLMs be available to run in your local machine when they start squeezing more data into uh, from the quantized types. And that was the kind of problem with Tornado that we didn't have before to think so much about the data management.
Before it was different product. Now you have two products. You have Tornado CPU edition and Tornado memory edition, right? More or less, or because you have a CPU accelerator and now how to call it LLM accelerator, because this is like, yeah, right.
I wouldn't call it an LLM accelerator, but I would call it that now is mature enough to be able to express and more memory bound pipelines. So now with the addition of the persist and consume API, and also with some extensions that we did in runtime level and our VM, how to manage allocation and deallocations of the objects on the device. Let's say that Tornado does much better work into memory management, and you can express these kind of things now.
But
and LLMs is an example. Yes.
The persistent consumer API in Java, it is translated to CUDA, native CUDA operations, right?
No, it's not translated to CUDA. The only thing that this API is translated is that in our VM, so when we generate the bytecodes, so Tornado, it has its own, let's say, set of bytecodes, so in VM, its own interpreter. So the only difference is that when we issue the bytecodes for persist and consume, what's happening is that when we issue a bytecode for persist, is that we prevent the VM to do the allocation. So it says execute the kernel on the device, and then even if you don't copy out the data, don't perform a deallocation automatically. So just keep the data on the device. And the consume, what is doing under the hood is that instead of copying the data and on the native level passing the pointer to the array, is that instead of passing the pointer from the object that you are copying from the host, we just pass the pointer that we have persisted before. So it's not a CUDA specific. It's like a point how we pass the pointers on the kernel. So,
yeah. So what I understood, you have the operations in Tornado with the data types. They are translated because it's Java to bytecode, and you have like a translation layer which communicates with the GPUs and CUDAs. And the first time, if the first kernel was done, what the operation did, it just copied the data, as instantiated this in Java data structure, and you could use it. And if you are for loop, you would immediately send it back to the next loop. And with consume and persist API, it is actually simpler because there is no allocations. The consumer just gets a pointer and doesn't even know that the data is already there, right? So it is like per reference. So before was per value, was copy, and now it's per reference.
Exactly. Yes. And also this what's happening now. This is that it gives you the ability, for example, to have more complex pipelines. So you can have, let's say, two different task graphs. A task graph A that mutates the data in a way, and then task graph B that mutates some other data, and then have the outputs of two tasks, both of them persist, and consume them from a third task graph. And in this way, you can express more and more complex pipelines without having this pressure in the memory and having to copy back or everything in the device and then copy it to the GPU. So it feels much more natural for a GPU programmer now to implement these kind of things.
So you could actually have something like load balancing almost, right? If you have two GPUs, you could do the consumer persist on one and copy data between GPUs, right? If you would like, in theory.
In theory, yes.
Just from my understanding, because they would be two independent, and you could copy the data one to Tornado and then back to the other one, right?
Yes, and in theory, an extension for that, we could use it for having, let's say, distributed inference, because
exactly
now with Llama 4 models, with 400 billion parameters, you go beyond the single CPU for inference. So it's the kind of this kind of concepts. It can be used, to have the inference distributed with Tornado in the future. Yeah, for sure.
Yeah. And so it means if you use Tornado and you would use Python or C, the performance has to be the same for the inference, right? Because this is just the initial copy and back, and the
the performance for the copies, yes, but then if you think about runtime performance of the inference, then it also you need to take into account the kernels, because the kernels that we generate. But the I/O should be the same, yes.
Yeah, because C would, if C creates the same graph and Tornado creates the same graph, the GPU performance is the same, and there will be the only remaining difference between the GPU inferences or the inferences what you do in Java before and after, right? So because anything else is like offloaded to GPU.
Yeah.
But it's a huge news, no? I mean, what it means is you can have with Java right now native GPU performance for inference.
Well, it's not native yet because it influences about from the cheat compiler. Because what we're doing is that we cheat compile the code, the kernels. So we have some indirections there, but it's very close to native performance. So if someone gets Tornado and not a highly optimized CUDA, let's say, that is written from an experienced CUDA programmer and does, all the optimization tricks, and it's something that it's very optimized. Yes, the performance is comparable for pure inference.
But if I would do it in C or with Python, then the PyTorch or whatever framework will create a graph for me, and they will optimize the CUDA, right?
Yes, but yes, that's a different story, because if you go to this direction, then most likely the code that is going to be executed onto the GPU is going to be highly optimized. So, or for example, if you use Llama, or Llama C++, the CUDA backend, if someone opens the implementation for them, they would see that it's a highly optimized manual kernels, that they have one kernel for each permutation of the input data. So you would see that you have one kernel for matrix multiplication for FP16 with FP32, one for int8 with FP16. So they have one implementation for each possible combination. So it's not that dynamic. But Tornado, what it does that if you try to do inference for FP32, it's gonna JIT compile a PTX code or OpenCL code for FP32. So that's why the performance for us is not comparable, let's say, to a manually optimized CUDA implementation at this point, because we have this kind of dynamic aspect to JIT compile based on the input of your model. So we don't have manually tuning the kernels.
But this is the same story we had already in Java, right? In the beginning, C was static and highly optimized, and Java was slower because the JIT compiler created simple bytecode, and over time the optimizations got better and better. And not speaking about GPU, just standard Java, and now they are sometimes faster, or if not, is a little bit slower than C. So the same could happen in theory in Tornado, right? So if you the more you do, the JIT could optimized because this the question is, can such a thing happen on this level as well, or?
Yeah, actually, this is what we're doing right now. So we have this performance that we have reported in the README. So we tested in different machines with OpenCL PTX, and we have reported the kind of tokens. So now we have people working from our team on try to see how we can squeeze a bit more performance, for example, in our CUDA PTX backend. So now what we're trying to see is that we are doing some, let's say, design space exploration to understand why we get some specific, let's say, performance for our PTX compared to CUDA PTX. So when someone gets a CUDA code, the CUDA compiler compiles the CUDA to PTX, which is the machine code, let's say, the assembly for CUDA, and then it compiles that to the GPU. And for us, Tornado generates directly PTX. So now we're doing some experiments and some performance analysis to understand how we can improve, let's say, our code generation for PTX, in order, when we compile the PTX code from Tornado to GPU with the NVIDIA tooling, to get the maximum from the optimization that the NVIDIA compiler does. And I believe that, in the next, let's say, 6 months, with the improvements that we're gonna do, the performance for inference is gonna be increased even further for the PTX backend for sure.
And this is the highly optimized static code is not open source, I guess, right?
It is actually. It depends from the framework that you are using. So, for example, TensorRT, which is a library from CUDA, which is proprietary, you don't have access to the kernel. And what it does actually, it's very interesting, because when you are passing a model to TensorRT and you want to run it on your GPU, what it does under the hood is that it statically analyzes the model, and it doesn't generate CUDA code, but it's a, let's say, a glue layer for the NVIDIA libraries. So it's gonna do some static analysis on your model and decompose it into different, let's say, computations. Say, okay, I'm gonna invoke this CUDA library from cuPlus, which is a library for NVIDIA for linear algebra. I'm gonna invoke this kernel for Catlas, which is a library from CUDA just for matrix multiplications. And it does this kind of pattern matching between the kernels, and it does the invocation to the libraries. And that's why, for example, the NVIDIA TensorRT the performance is great for the models. But when you are looking into the inference and you go to Llama C++, for example, or other implementations, they are open source. So inside the source code, you would see that they have implementation for different backends, like OpenCL, CUDA, Metal that we discussed the previous time about, which is the first-class citizen support for the Apple, and they have all the kernels available there. So you can see how they implement things. And actually for us, we deep dive into it and we got inspiration on how to express some things in Tornado. Because if someone now open the layer planner, how we implement the inference in Tornado and look into the matrix vector, it would assemble for them a lot how you would express this kind of optimization in CUDA, because we do things like using the shared memory of the GPU and doing some tiling to preload data and apply the computation. So many of the concepts that one would see in the Tornado kernel level optimization, they're originated from CUDA implementation or OpenCL implementation that are open source, which are just expressed with the Tornado API.
Also, a crazy idea. What you could actually do is use LLMs for the optimization, right? For every kernel.
Actually, we do that.
Okay.
And yes, so we do that. And personally, because I worked on developing the kernel for Tornado, I used Claude for that. And sometimes it works, sometimes it doesn't work. But what I found myself doing at some point is that getting CUDA kernels highly optimized and putting also in the context of the LLM Tornado kernels that we have in the unit test, highly optimized. And I was saying that this is TornadoVM, this is the API of Tornado, this is how you express optimization of Tornado, this is a CUDA version. Can you try to adapt the kernels? And after a couple of iterations, sometimes the results were amazing. And I didn't expect that you were able to do this kind of things.
Yeah, also doing this, but sometimes it seems like, as not this what you are doing in my projects, but sometimes it doesn't get the context right? It ignores the context, so you have to be explicit, or it doesn't ignore, it ignores the spec. This was my case, so I had explicitly said, okay, this is the context, this and this and this, and sometimes a link was not enough, because you could have an agent, right? So a for loop do as long as there's
exactly. So this is one of the projects that we started in Manchester right now. So we try to build an infrastructure to optimize Tornado kernels on the GPU that it's gonna run to. So we're gonna have, let's say, an MCP server, and we're gonna generate from Java Tornado kernels, and on the fly try to iterate until we hit some performance benchmarks and some performance evaluation. So it's crazy the fact that you're gonna be able to do that from Java. So imagine that you're gonna optimize the GPU code that it's gonna run on the same GPU from just a local MCP server. Yeah. So now that we have all this kind of experience and all the infrastructure ready, it's very easy to try to experiment with this kind of things.
Yeah, I think the result will be great. So I'm pretty sure with that infrastructure in place is more fun, you are more productive, and maybe you will find even better optimizations what are available right now, because you are with TornadoVM, you have already the abstractions, and you have already the wisdom or the knowledge, the experience from the community, and maybe you will find even better optimizations, right?
Exactly, and we have all the things to provide the feedback loop, let's say, to an MCP server. So we have API, we generate the kernel, we have profilers to get the metrics and feedback. So for what LLMs are doing great, this is more than enough in order to set up this agent and improve things much faster. And also, personally, what I found is that it's very easy to build, let's say, testing infrastructure with LLMs. So creating unit tests and very small permutations between unit tests in just a matter of minutes and just test it. So I think
but you have to be very specific with the prompting. Then it is almost if you say, okay, write this and test, otherwise it is unusable, right? So if you
exactly, yes. But if you're specific, if you know what you're doing and you know the shape of what you expect, I think it can speed up things much faster. And,
if you know what you are doing and if you can read code fast, it's crazy. This is like the super accelerator. But I think my opinion is that this only suitable for disciplined junior developers. If they really would like to learn, it's perfect. But if you just do something and it generates lots of code, you are lost in the second iteration, I would say.
Yeah. Personally, I don't know. For us, even with my generation, that we have access to internet and Stack Overflow. You had to pay the price and spend the effort of debugging, try different things. I don't know a junior developer that it's gonna start, writing code in 2025. How it's gonna be for them to, learn the process of debugging and searching for things, trying different and not just working. Yeah.
Interesting.
That would be interesting. Yeah.
Are you aware of Brock AI? BROKK AI?
Brock or Grok?
Brock. B. Like this is a dwarf which does the hammer from. Jonathan Edith from the Cassandra project or JVector, he created a startup on this interesting project. This is a tool written in Java, and this is something like Cursor or Bot, almost no IDE. And you can just with context generate code completely. And what it also does is interesting concept. If a Maven project with dependencies, what Brock does, it decompiles the code to get more context and uses an ASTs and learn from the context. You can generate even better Java code. So it's open source. It's called Brock. So you can look at this. So this is interesting. And one question regarding hardware. Are you aware of TENS torrent?
Yes.
Is it usable?
I think they have prototypes that they run. Yes.
Yeah, because this is like a way to have a GPU accelerator, right? And which is NVIDIA compatible almost, right?
Yeah, there are many companies in this. Personally, well, before coming back to Manchester, I worked in a company that they were doing compilers for AI, so I have a bit of experience. The problem with the companies that are doing this kind of hardware is that you have a lot of them. So if one searches online right now, they can find like, let's say 10, that they go from very small, tiny, let's say, very domain-specific hardware that they intend to do inference on the engine to Tensor or to TPUs. The problem usually it's not the hardware, but usually it's the software, and that's why NVIDIA is dominating the whole, let's say, domain right now. Is that because not just the hardware is great, but the software is great. So you have support. It's very mature. You have all the tooling infrastructure from very low level profiling and to understand if you are experienced, let's say, GPU programmer, to very high level libraries that they just work, like TensorRT, that you just pass the model and they run optimized code. So yes.
Okay.
The answer is yes, but if you want to use this kind of hardware like Tensor in production, then you need to think more about the software problems and limitations that you might face other than performance that you're going to get from the hardware.
Because it could be one of the also your time is of course limited, but TornadoVM could provide support for such a thing, right? So okay, then
yes, in theory, yes, it can be a layer on top and just have a different package and have a different package for a different hardware. Yes,
this is what I thought.
This is what we do right now in a way. So we have packets for OpenCL, PV, PTX, so from different vendors, and now we start working on the backend for Metal for Apple. So in theory, because the infrastructure is ready, is modular, it can be extended. You can add a custom hardware accelerator to Tornado.
So this is not. This is so I'm really interested in the Metal. What do you think about performance? Would it be similar to CUDA or just your feeling? It's not like I'm just curious.
my feeling, let's say, is that as I mentioned in the last podcast, is that now the GPU Llama in Tornado they run through OpenCL to Metal, which to M Silicon, which is great if you want to do local development and then you want to deploy Tornado for inference into a server with GPUs. The let's say the pipeline and the process for you is going to be the same. So it's very easy for the development to do something locally and then deploy it on the server for NVIDIA GPUs. However, the performance is not great for us. And this kind of mental exercise that we're doing for PTX that I mentioned before, we did it for M Silicon. And the thing is, what's happening is that OpenCL have been deprecated from Apple's side of things for quite some time. So our assumption is that the driver doesn't perform any optimization. So our kernels that I mentioned for inference, for example, they use local memory, which is the cache on the GPU, on the cores of the GPU. We do some other things like optimizing the number of threads that we're going to deploy. And we did some experiments running things with and without optimization from Tornado, and we found out the performance is the same. So even if you write a kernel which is highly optimized for OpenCL and you get performance for AMD, NVIDIA, Intel, if you run the same thing on M Silicon, the performance is the same. So we believe that once we migrate to Metal, because we're going to use the latest, let's say, compile and drive infrastructure from M Silicon, we're going to start seeing the performance we expect, because they have first-class citizen support for expressing caches, using the caches, doing the thread scheduling, things that we get for free for other architectures. We're going to start seeing this performance for Metal as well. So I believe that once we have this ready, the performance is going to be much improved on M Silicon devices compared with what you see right now.
And is it hard to implement the Metal, or?
No, because we have already an OpenCL backend, and if one looks into the semantics of the Metal, is just another, let's say, incarnation of OpenCL. So many things you would see that they are looking very OpenCL-like. So for us, I believe we just started this project, but it's not going to take so much because it assembles a lot the compilation pipeline that we have for OpenCL. So for us, it's going to be tricky to achieve the code generation, but it's not like a different, let's say, a different ISA like PTX or this kind of thing. So it shouldn't take that long.
So when can I invite you back to talk about Metal? When we should schedule the first meeting?
Let's hope that. I think our goal is that in about, let's say, 6-7 months from now, to have a GPU Llama running for Llama 3 that runs already Mistral. Now we have almost we're about to release Gwen 3 support, and JMFI, Metal, and we're adding types for int8 and Metal. So let's say that in 6 months from now, the GPU Llama is going to be much more mature, and hopefully we're going to have a demo with Quarkus, Langchain4j, and GPU Llama running. Yeah.
So this is like almost Christmas. So we get Metal for Christmas.
Yes, let's go for it. Yes.
Yeah. Perfect. Yeah. Great. So now I understood, and I think one of the most important projects in Java ecosystem right now, what they are doing, if this works, it is a huge game changer. And yeah.
Yes, I think the Llama use case for us, it's if someone wants to, do a quick startup with Tornado, if they take a look into the source code and what we have online for GPU Llama, they would understand that it's something that it can be used, it's mature, it's very easy to express things. So I think, yes, we're getting there.
Thank you. Where people can find you, the listeners, on the internet and projects?
Yes, so I'm in Twitter, X, GitHub, and it's Mike Papadim. So, yes.
And TornadoVM is the project where you find on GitHub, right?
Yes, Tornado is on GitHub. We have a website. If someone types TornadoVM on Google, most likely it's going to be the first
And
hit.
the
So, yeah.
project we talk about was GPU Llama. This is a repository with example, right?
Yes, it's called GPU Llama 3.
Yeah.
.java. Yeah.
Perfect. Thank you. I wish you the best summer. No vacations.
Thank you.
Just work on metal. And we see then Christmas.
Yes, thank you. Have a good day.
Thank you.